Hello, y'all. Welcome to lesson 124 of my DP chemistry curriculum. Today we're going over reactivity 3.3.3, which basically discusses radicals, how they take part in substitution reactions with alkanes, producing a mixture of products. So we're going to explain using equations the propagation and termination steps in the reactions between alkanes and halogens. We already learned a little bit about the initiation step in the previous unit, so we're just going to extend that further into substitutions with radicals in alkanes. So generally with alkanes, we note that for the most part, they are pretty unreactive. So we can write that down, are generally unreactive. And that's pretty much due to two basic reasons. So the first one being that they are mostly nonpolar or comprised of mostly nonpolar bonds. What that means is in an alkane, there is a kind of limit to attractive forces, things that can break those bonds. And that's because they're pretty much only LDFs. Usually only London dispersion forces are going to be the major attractive force, but that's not as strong as hydrogen bonding or dipole-dipole. We have none of that polar or polarity that will cause bonds to be broken and new ones to form. Furthermore, they have relatively stable bonds. So what I mean by that is when we look at the carbon-carbon or carbon-hydrogen bond, those have pretty high bond enthalpies, 380s, 400s, etc. And so they're going to be hard to break most often. So how do we actually react with them? Well, generally, alkanes will undergo substitution. And this is how we can interact with them, but it's specifically substitution through radicals. As we mentioned earlier, radicals are highly reactive. Oops. Radicals are highly reactive. And they can overcome the unreactivity of alkanes. In fact, they'll react with pretty much anything. So they will generally force that reaction. And what we'll end up with is usually a halogeno alkane product. So let's go ahead and look at just a sample reaction. We might have something simply like methane, which we know as CH4 gas, and it can react with chlorine. And there are many steps involved, but we'll just cut straight to the chase, and we will make CH3Cl chloromethane plus hydrochloric acid. And so this is a reaction that we might end up forming at the end of this section. And we can see that we have substituted one of the hydrogens in methane with a chlorine to make that chloromethane. This is where we get the name substitution. This usually occurs in 3 steps. So as we look at the substitution of alkanes, we have our first step, which we learned in our last section, as initiation. Initiation simply being the formation of a radical. Following initiation, we're going to have propagation. We discussed propagation a little bit as we looked at how radicals can deplete the ozone layer, and we're going to explain that a little more in this section. And that's basically where a radical reacts with a covalent species to form a new species and a radical. So this is what we mean by propagation, because with new radical, we can now repeat the propagation step. So this creates a chain reaction. So these radicals can just repeat forming new radicals while forming new compounds, and this is why we call it propagation. It's just propagating itself. So how does this finally end? Well, it ends with step 3, which is termination. Termination is simply two radicals react to form a covalent bond. So it basically ends when one radical will meet another radical instead of a covalent compound, and instead they'll just both cancel each other out by creating that bond. So what we need to be able to do is explain these 3 steps, and we have to do that using reaction mechanisms. So we'll do examples with reaction mechanisms. It's important to see how the electrons within these radicals propagate themselves through the reactions and move and transfer from bonds to lone electrons and back to bonds. So let's go ahead and look at our first step, initiation. We looked at this step in our last video, where basically we have some halogen, like chlorine gas, reacts with UV radiation to form 2 chlorine radicals. And what we do is we're going to use our fishhook arrows to represent the electrons in that bond splitting evenly through homolytic fission to go to each chlorine respectively. Once we have our radical, we can move on to our propagation step. And so we might look at that methane reaction we saw earlier, where we have methane plus a chlorine radical. Now, this is where we really want to get used to using these fishhook arrows to show the reaction mechanism. This radical will react with a bond in between the carbon and hydrogen. By doing that, it's going to force one of those electrons out of the bond. The other electron left in the bond will then move on to the carbon. You'll notice I specifically make my arrow go from the bond onto the carbon. That shows us that the electron will stay on the carbon, not any of the other hydrogens. This will produce a methane or an alkyl radical plus HCl. So we have that new covalent bond there. That is one step in propagation. But the issue is this compound here is now a radical that can continue and propagate further reactions. In fact, it may react with another chlorine molecule. And so we get CH3 radical plus a chlorine. And now once again, this is going to react with an electron in the bond, and the other electron will move to the chlorine. Thus we have chloromethane plus another chlorine radical, which can cause the same sort of chaos. So this effect can continue almost endlessly, and that's that chain reaction, because we'll always end up with another radical. In fact, this radical may attack a chloromethane, and maybe it will displace the chlorine again, forming chlorine gas. It might displace another hydrogen, creating now a chloromethane radical with another HCl. So it can form any number of species, or maybe we have 2 of these, which now can become a radical and then react with one another. These steps can continue on and on until we eventually reach termination. Termination, we may look at our alkyl radical plus the chlorine radical we just formed. And in this case, these 2 electrons can meet, they can bond, or create that bond, which ends us with chloromethane. And there we have the end of not just 1, but 2 radicals. Furthermore, we may just have two chlorine radicals, which after becoming separated, just end up re-reacting with one another, forming chlorine. And once again, we'll show these fishhook arrows to show the movement of electrons. Now, one thing you'll notice is that often in propagation, the one radical we pretty much never form is hydrogen. So we generally make halogen or alkyl radicals, not hydrogen. We don't do that one. Hydrogen as a radical is highly unstable. It will immediately dissipate, while these other radicals can move around and continue propagation further on. Hopefully this helps. It helps you understand a little more about substitution, as we'll see that like we just go from a methane early on in our propagation early step, and we substitute in a chlorine. So we can kind of get that substitution. We're replacing a hydrogen with a chlorine. So this is where that comes from. So hopefully this helps, and have a great day.